Welcome to part 2 of my coverage on organic nomenclature, and we will concentrate on the principal groups from alcohols to carboxylic acids. Now, I highly recommend that you first watch part 1 because most of the fundamental rules are found there. And I dare say that if you don't master the essentials of part 1, you'll be getting wrong answers more than 3/4 of the time for most of our cases here. And what were the rules that we actually were able to discuss before? I can divide it into 4 parts, and we start with the parent or the root chain. And normally, the parent chain is simply the longest chain. And most of the time, even in this recording, we would consider the longest chain as basically the parent. Now, I'm just saying that because in the third part, on the next installment, there are actually a lot of dilemmas that we will not yet discuss, but sometimes it's just the parent is not as easy to pick. Okay? For the locant determination, we have 3 rules and they have a certain priority. The most important rule is that if I have a principal functional group, then we give it the lowest we give it the lowest locant or number. Now, if there's no principal group, like all our low priority substituents, we follow the first point of difference. Or in the case that I have multiple principal groups of the same type, and I've discussed FPD a lot during part 1. And the last tiebreaker is alphabetical order. So meaning if 1 and 2 do not apply, then we have number 3. We just alphabetize, and whichever goes first in the alphabet will get the lowest number. Once we write the name of the organic compound, we have several reminders. Use multiplicity prefixes for several substituents of same type, like prefixes like di, tri, tetra, and so on. Now, once you have multiple prefixes, you alphabetize them. Of course, not considering the multiplicity prefixes. And in the case that I have 2 consonants, that's between the parent and the suffix, then I have to add a vowel in between, which is usually the original vowel. Now, for the suffix, I want to clarify once again that although we have the suffixes "-in", "in", and "-ine" for the hydrocarbons, the real suffix is letter E. Because even if I have a double bond and I have a new principal group and I replace the letter E, these fragments or these letters still remain. And you will see this a lot, observe this a lot as we go through the examples. Without further ado, let's go to the examples right away. For 37, this is rather easy. That's why I didn't have a circle over this one. So we should answer this quickly. The parent chain is just 4 carbons. All are single bonded, so we have AN. And usually we end with E, as butane. But since we have here a principal group, and we have a suffix for OH for alcohols, then we replace letter E with all. But now, once you have a functional group, that's a substituent still, you need to indicate the position. And it's sensical that we start from here instead of this side, because if I start here, I will be able to assign the smaller number to OH, which is number 2, giving us the name butan to all. Or sometimes you can just put it at the start, like 2-butanol. Because if you start at the left, you get butan 3-ol, which is, of course, less preferred. 37, this is 38. We have here a cyclic compound, so we have the prefix cyclo, and it has 5 carbons, so that's pent. Now, we cannot use AN because there's literally a double bond, so we have to replace that with EN. But now, we have to remember that since EN, a double bond, is still a functional group, we have to indicate its position. In part 1, if you noticed, the double bond always gets number 1 simply because there's no higher ranking substituent than the double bond before. But now we have OH, which is of higher rank than the double bond. So this time things are different. Number 1 will now be assigned to the OH. We have no choice but to move forward, either here, number 2, and reaching reaching the double bond either way as number 3, whether you go top or bottom. So the double bond is apparently now at number 3. And then for OH, since it's at number 1, our convention is that we don't anymore write number 1 for a functional group that is placed at carbon number 1 for cyclic compounds. So this is the final name. Or of course, you can put this as the start, giving you the name 3-cyclopentanol. For 39, we have here a rather simple parent chain. It's a straight chain containing 5 carbons. No double bond, so I can just add AN. And of course, I cannot write E because OH is suffixable, meaning I instead use the suffix ol. As always, we need to indicate its number, and this time, what we need to realize is that OH is the principal group, chlorine is a low priority one, so we want to give the lowest number to OH. Meaning, between starting at the left and starting at the right, it's better to start at the left. So that means that OH would have number 2 as the locant. And in that sense, we have chlorine sitting on carbon number 4, so we will have that prefixed as 4-chloro. Now for 40, it's a little bit different because we now have two OHs and it's a tie. In this case, of course, we use the first point of difference. But here, whether you start from the left or the right, you get both 2, 4, or if I start from the right, it's 2, 4 still. Now, the tiebreaker is chlorine. We want the smaller number for chlorine because that's the only thing that will differentiate the starting point of left and right. And of course, if you start at the right, chlorine will gain the number 2, which is lower than when you start at the left. So that would be 2-chloro. And as with the previous item, we have 5 carbons. Then all are single bonded. And this time, since I have two OHs, I need to indicate their numbers, right? 2, 4. And of course, all is just a suffix that means a single OH. But we have two OHs, so apparently we have to, as usual, indicate that there are two of that by adding the multiplicity prefix di. So diols are basically compounds with two OH groups. Now, as you notice, we have two consonants here, and that's not allowed. So the vowel or the last thing we have here before is E. So now we have to restore it so that there's a vowel in between the two consonants. This would be the final name. For 41, and this is very, very interesting. In fact, this shouldn't be even in this list of things to name, but this is interesting. We'll have more of this in part 3. Normally, the first thing people would do with ORs is to find the parent chain, and that would be benzene. Since it's larger, I don't know, it's longer, but this time it's quite different because the parent chain is actually this, for the simple reason that this contains the principal group OH. And of course, we haven't encountered that before. The only thing we know is that the parent is the longest. But I'm just introducing this rule that it's not always the length that counts. It's the presence of the principal group in that chain that counts. So I'll elaborate more of that in the next installment of nomenclature. For now, we name this. So if I start from the right, we give OH the number 1. So this is the preferred starting point. Our bromine would be at 2, and our benzene would be at 3. Take note that when benzene becomes a substituent, we give this the prefix phenyl, as opposed to the, well, some people will call it benzyl, but benzyl is actually different. So we have a 3-phenyl and 2-bromo, and we can just start first with the parent containing 3 carbons. And of course, we suffix this as all, and you need to, as always, indicate the position of the OH. In this case, it's number 1. And we have here a bromo, B, and phenyl, P. Alphabetization tells us you start with bromo. That's 2-bromo, and then 3-phenyl. And this is the final name. Okay? For 42, now we start with a new class of compounds. We have the amines, right? Because if you have NH2, you call that an amine. Now, this is simple because all you need to do is to count the parent chain. 1, 2, 3, 4, 5, 6, 7. So 7 is hept. Then all are single bonded, so that's an. And the suffix is simply amine. And actually, I forgot to indicate the number. The number should be here. 1, 2. So our number for the amine should be 3. So it's heptan 3-amine or 3-heptanamine, whatever. 43 is quite interesting because I have here an amino group still. It's just that one of the H's have been replaced. And the nitrogen has 2 carbons attached to it, this one and this one. So I have 2 potential parents. This one, which has 2 carbons, and this one, which also has 2 carbons. It's kind of a tie. So like the parent is usually the longest. Now I have 2 chains that that are equally long, what do I choose? Well, the tiebreaker is, well, usually you pick the one with the principal group, but both are attached to the principal group. What's your next choice? Find the one with the more functional groups. In this case, double bond is a functional group, right? So in this case, this would have more of weight compared to the one here. So this would be our parent chain. So that would be two carbons with a double bond En. And of course, we should remember that we have here a suffixable group, which is amine. So that would be ephenamine. But ephenamine only refers to this part. We still haven't included this in the name. So this is an ethyl group, right? So in order to indicate that I have an ethyl group that is attached to my nitrogen, we indicate the prefix N, what's this, two carbons, ethyl. So now, this is an interesting locant because so far, you've been accustomed that a locant is a number. But not all the time. Because here, it's like I have no choice but to indicate the letter N just to make sure that my ethyl is not attached to this part, but instead this nitrogen. For 44, it's almost the same case. So here, there's not a lot of competition. Our parent chain is this benzene because it still contains the amino group. So it would have the name benzene amine. And actually, an additional rule on our vowels and consonants, if there are two vowels, we eliminate the first one. So it's like benzenamine. But now, how do I indicate that I have two methyls? If a while ago, to indicate I have an ethyl, I have N-ethyl. What if I have two methyls? Then we have here, right when we have two methyls, we just write dimethyl. How about the locant? Where are they attached? Once again, to the nitrogen. So you have to write N. And remember, di means you have to write two locants. So we will now call this N dimethyl benzenamine. Okay? 45 is actually incorrect. This one has 5 bonds, but maybe we can just remove this. Yeah. All right. Just to make things more interesting. So now I have here my parent chain without a doubt because this has the only carbons we have here. And how many carbons do we have here? 1, 2, 3, 4, 5. So that's pent. And then we have a triple bond. And I think that would be at number 1 because this is also the carbon that contains NH2. So that would be pent 1 ion. And here we also have to indicate that my amine group is at number 1. So that's pent 1 ion, 1 amine. I have a triple bond at this carbon. I have an amino group also at this carbon. I just need to indicate the presence of the chloro. Its carbon number would be 1, 2, 3, 4, 4. So that would be 4 chloro, pent 1 ion, 1 amine. Of course, once again, you can put this at the start, giving it the name 4-chloro, 1-pentyne, 1-amine, but it's really up to preference. 46 and 47, we'll just have these two examples of sulfur analogues. So remember, when we have an SH, we call that a thiol, and easily enough, the suffix of a thiol is also thiol. So for example, you have here 5 carbons, so that's pent, and then no double bond, so an. And then our thiol is apparently this one at number 2, so that's pentan 2 thiol. But once again, look at this. I have two consonants, so we removed E here for thiol, but in this case, we have to restore the vowel just to make sure the two consonants don't bang up to each other. So that's the final name, pentane 2 thiol. In this case, it's interesting because you call this a thioether. Okay, just a refresher, I guess, wherein I have a sulfur with 2 carbons. So now, as with the previous example, we have here 5 carbons, so that's the same thing, pentane. But look at this. I now end with E because a thioether group like this one, just like an ether, is a low priority substituent. So how do I call this? Well, this is an ethyl. Then sulfur, we usually use the prefix thio. We just call it as it is, ethyl thio. And this ethyl thio group is attached to carbon number 2, just like the previous item. So that would be 2 ethyl thio pentane. It has an asterisk because this is somewhat higher level than most of the examples we will have. And this is just an introduction for part 3. I thought I would introduce this now that we know how to name alcohols and amines. There are cases that you have a compound which has more than one principal group, in this case 2, OH and NH2. What we know is that principal groups occupy the suffix, but one thing you should know is that if I have 2 or more principal groups, only one will be suffixed, and the rest will be prefixed. So what will be the suffixed one? That is the highest priority group. Or in this case, OH versus NH2, the winner is OH. So we will use the suffix for alcohols, which is ol. And therefore, we will give this the lower number, meaning it's better to start off at this carbon than at the other end. So we give OH number 2, and we have NH2, if you count properly, number 4. And the prefix for NH2 is simply amino. So its complete name would be, well, we have the prefix first, for amino, and then our parent has 5 carbons total if you count, pent, no double or triple bond, so we just add AN, and then of course we indicate the number of the OH. Now, two questions may arise. First, maybe, how did you know that OH is of higher rank than NH2? And the answer is simply, you have to memorize that. But there are tricks to make it easier to remember. We'll discuss more of that in part 3, along with the prefixes, because the actual specific prefixes are also to be memorized. So we go back to some more simple examples for the moment. So 49, we now transition to the functional groups that contain C double bond O. Or if you remember from the previous videos, we call this the carbonyl group. So if I have a carbonyl group between two carbons, remember we call that a ketone. And the suffix for those are or is ONE, like own. Okay? So here we have 4 carbons. None of those carbons are double bonded. The only double bond here is to the oxygen. And instead of ending with the usual letter E, we end with O. But of course, since the carbonyl group is still a functional group, you need to indicate its number. By practice, I mean, imagine, we already have like 40 plus examples so far. You should know that this would be at number 2. So we have butan to own, or as you know it, you can put number 2 at the start. 2-butanol is also acceptable. For 50, we have your cyclic compound containing 6 carbons with a double bond. And remember that double bond is actually lower in priority than most other functional groups. So unfortunately, the ketone would be higher in ranking, and that would give our double bond the this 1, this is 2, this would be number 3. We will also have the same fate if we went the other direction. So that would be the double bond at number 3, and we can just use the suffix on, because remember, if we have the double bond, I mean any functional group at number 1 in a cyclic compound, we don't need to write the number 1. For 51, we have 2 carbonyl groups, and those are both ketones. If you double check, those are both between 2 carbons, okay, each. So instead of just ending with ONE, to indicate we have 2 of them, as usual, we add the multiplicity prefix di. And we have 6 carbons for the parent chain, so hexane. Okay, well, I already put AN because there's no carbon-carbon double bond anyway. And our numbers for the carbonyl group would be best to be 2 and 4, right? So that would be 2, 4, diol. Remember, we have 2 consonants, N and D, so in this case, we put a vowel. Well, usually we had an E here before we removed it, so I think it's logical to just return it. Okay, so we have hexane 2, 4, diol, or 2, 4, hexane diol. You can put the numbers at the start as always. For 52, we have the benzene ring, but one thing that you have learned so far, like number 41, is that uh, the benzene ring does not have the principal group, then this does not become the parent chain. The parent chain would be this one, even if it's shorter, because it contains the carbonyl group. So this would be our parent chain, and we would still prefer to give the carbonyl the lower number, so we start here at numbering, then this is 2. And therefore, at number 4, that's where we find our benzene ring, which, remember, we call this as the phenyl group as a prefix. So to assemble it, we have 4 phenyl and then 4 carbons in this parent chain. Bute, no double bond there, and then you still need to indicate the number 2. Or again, you can write that as 4 phenyl 2 butanol. Now, we go to aldehydes, as you can see, because once you have a carbonyl group wherein only one is a carbon and one, instead of being another carbon, is a hydrogen, that's an aldehyde. Remember that. And the suffix for aldehydes is simply al, like aldehyde. So in this case, this is very simple. We have four carbons, no double bond, so I can just add an, and then let's just end with the suffix al. Now, one thing that you may notice, I don't know if you were able to quickly spot that, was I didn't even write number 1. And this is not even cyclic, right? You notice that if I have compounds that are not cyclic, I'm usually forced to write the number. But this is quite different from aldehydes all the way to the next functional groups, because these are what you call as terminal functional groups. It would actually take a lot of talking, it would exhaust us a lot to explain why, but the point is, aldehydes and other functional groups later are terminal, meaning you can always find those groups only at the end. And that would give us always carbon of that group as number 1. So there's no point in adding butan 1-al when we already know that aldehydes will always have their carbon at number 1 for the aldehyde group. The same with 54. You notice that I have two ends, and that's where we find the two aldehyde groups. And notice that the H here is hidden, but of course that doesn't mean it's not there. So if I draw it completely, it will be like that. So if we have an Al as the suffix for aldehydes, if I have two of them, I mean one on each end, then the same thing. We just add the multiplicity prefix di. And we have 1, 2, 3, 4, 5. So we have 5 carbons spent, and then no double bond between carbons, so AN. And you notice that, again, we have here the same scenario as a while ago. We have two consonants. Let's just return the letter E. And once again, since the aldehyde groups, the formyl groups, are found at both ends, we assume that if I have two of them, one would be on number 1 and one would be at the last carbon, which in this case is number 5. For 55, we have a cyclic aldehyde, and this is going to be a little bit different in terms of naming, because instead of just ending with the suffix al, we have quite a long prefix here, I mean a suffix, and that is carbaldehyde. And this is mandated by the IUPAC, so we can't really do anything about it. So we have the carbaldehyde suffix for this one in cyclic aldehydes. And then our cyclic compound is cyclo, we have 5 carbons spent, and then notice I still put the letter E because if I don't, I would have N and C, which are both consonants. And of course, for like how many times already I've told you that that is not acceptable. So in this case, the aldehyde group would be situated at number 1, okay? And that means our chlorine is situated at number 2. So we need to add the prefix to chloro. Now, for 56, I actually already wrote the answer because it would take a lot of processing for us to be able to arrive with the complete name. But I want you to make this an exercise. You can pause this and then try to reason out why all of these things make sense. Now, I'm going to explain it if you don't want to pause. And let's start off with this one. Diene, dien because I have two double bonds. Al, of course, because of the aldehyde group. Hexa because I have 6 carbons, 1, 2, 3, 4, 5, 6. Okay. And notice I still make sure that my vowels and consonants are beside each other. Then 5-methoxy, that's already obvious at this stage. Okay. Now we move to, we're now done with ketones and aldehydes in this slide. We find ourselves moving from one functional group to another. We're done with ketones and aldehydes, and now we proceed to carboxylic acids and the carboxylic acid derivatives. And they are terminal functional groups, meaning there's a difference in the suffix of the linear and the cyclic versions. Okay? As a rule of thumb, the cyclic suffixes are much longer than the linear suffixes. And this will take a toll, this will take some time, so I think you should be prepared for what's to come. Okay? So in 57, we have a simple carboxylic acid. Okay? We have 4 carbons in the parent. None of those carbons are double bonded to each other. So that's just AN. And then the suffix for carboxylic acids is just oic acid. That's the final name. And that's the final name. You don't need to add number 1, like butan 1 oic acid, because just like aldehydes, carboxyl groups are terminal. Okay? And the same applies to all other derivatives like esters, amides, anhydrides. So locants are not much of a thing for the examples in the next slides, just like this one. 58, we just have two carboxyl groups. So just like for aldehydes, you proceed with the same suffix, oic acid. You just add the prefix di to indicate there are two of them, one on each end. And I have a total of 4 carbons. Again, no carbon-carbon double bond. And two consonants, you know what to do. You add the vowel. You just put back the E. So this is the final name, butane dioic acid. 59, we have a cyclic compound, and therefore I just mentioned like a few moments ago that the suffix will change. Okay, so we have the COOH attached to, apparently this is carbon number 1 of the parent, and the parent is cyclohexene, right? Because we have a double bond. So, and this time you have to indicate that the double bond is at number 2. Okay, and then of course, I told you that the suffix will change because we now have a cyclic compound. So instead of just using oic acid, this is funny, the suffix is simply carboxylic acid. Yeah, like the entire thing, the entire name. And if I do that, I have two consonants here. I need to put letter E in the middle. And don't forget, we have a methyl group here. If we count properly, this would be 1, 2, 3, 4, 5. So that is a 5-methyl substituent. This is the complete name. 60, we have benzene, but just like in our case for 52, our benzene does not have the principal group, but instead, this one has the principal group. So apparently, this is going to be another phenol substituent situated at carbon number, this is 1, this is 2, this is 3. So that's 3 phenol, and then I have a double bond at 2. My parent has 3 carbons, and I have COOH. Now, if you can assemble all of that together in your mind, you could already come out with the final name. And this takes practice. I mean, I've been doing this for quite a while already, so I can easily do it on my mind. But of course, you can do it step by step at the moment. So even if you check, this is the complete name. Like, we followed all rules. Correct locant, 3 carbons. I made sure that vowels and consonants are beside each other, the double bond position, and then the suffix. Yeah. It's something that you can obtain over time if you keep on practicing. 61. We're actually proceeding to already the first derivative. This is not anymore carboxylic acid, right? Because it's not anymore COOH. It's now COOC or COOR. Remember, we call them as esters. Esters are a little tricky to name because esters have two parts in their name. The general format is alkyl alkanoate. Okay? And therefore, you have to recognize which part of the structure is the alkyl and which part is the alkanoate. In order to do that, find the two oxygens of the ester, the double bonded one, which is actually the carbonyl group, and then the single bonded one. Make a divider here. Okay? Now, the half which contains which has the single bonded oxygen will be the alkyl part, and then the other half which contains the carbonyl group is the alkanoate part. So let's practice that. My alkyl part contains 1 carbon, so that's methyl. And then the alkanoate part contains 2 carbons. Don't forget to count the carbon and carbon, okay? Do not exclude it. So that's 2 carbons, F anoate. Of course, again, we're assuming we have AN because there's no double bond here, no carbon-carbon double bond. Let's do the same thing in 62. This is the double bonded, this is the single bonded one, this is the line that connects them, cut. So this is the alkyl part, 2 carbons, ethyl, and then the OH part is branched. So actually you can start first with the parent, so 3 carbons, so that's prop, no double bond, then OH, and then take note that at the OH part, not the ethyl, okay? The ethyl doesn't have any substituent. At the OH part, you have a methyl. We didn't write this yet at number 2. So, you put 2-methyl immediately before the propanoate. Many would make this initial mistake of writing 2-methyl before the ethyl. But if you do that, you put this here on top. It's like saying my methyl is on the ethyl group, which of course is not the case. Let's do the same thing on 63. Find the ester. Oh, by the way, ignore this, okay? This is not an ester, ROR. This is an ether. So this is just a substituent, mind you. So don't notice this. The real ester is this one, COOR. And this is the double bonded, single bonded one, divide. Now, you notice that esters can actually be written like this because many people are accustomed that the double bonded one is on the left, the single bonded is on the right, but no one is preventing anyone from doing the opposite. So in this case, the alkyl would be this one, and the O8 would be this. So it's kind of switched. So the alkyl has 3 carbons, no double bond, so it's just propyl. And then my O8 is a little complicated because it has this methoxy, right? This is a methoxy group. So this is a methoxy something. Methoxy what? Well, my parent has 1, 2, 3, 4. So that's bute, no carbon-carbon double bond. So an O8. Then we have a methoxy at what? Remember, the carbonyl-carbon is always number 1. So this is 2, 3. So my methoxy is at number 3. So I write that 3-methoxy butanoate. Now we have an ester attached to a cyclic chain or a cyclic parent chain. Okay. This is different from esters where you actually find the COO part inside the ring. That's kind of advanced, so I won't even try to tell you what the name of that is. For now, we have this example. So this is the divider. Hopefully you already recognize that before I made this division. And this is the alkyl part, the right side, the O8 part is the left side. So the alkyl is a cyclopentane, so that would simply be cyclopentyl. And this is obviously cyclohexane. Now, if we follow the nomenclature for linear esters, we just have the suffix here, cyclohexanoate, right? But, well, the IUPAC says, no, you don't do that. So instead, you just write the entire thing, cyclohexane, and then the suffix, again, expected to be longer, is carboxylate. So from O8, it becomes carboxylate if you have a cyclic O8 part. Okay. Now, this is different. This example is quite different, and I don't know what's going on here. I did this after answering 65. This is interesting because even though our ester has a cyclic O8 part, our cyclic part here is benzene. In this case, we have a special suffix. We don't anymore use the entire thing carboxylate. This entire thing right here on the left side is called benzoate because you call the carboxylic acid with benzene as benzoic acid. And sometimes you're ought to break some rules. So in this case, we just call this as benzoate, not benzene carboxylate. Maybe it's acceptable, but I think this is more commonly used. And then the alkyl is just this part. Hopefully you recognize that. So that's just ethyl. So the entire name of this thing is just ethyl benzoate. Let me just remove this for a while. We're now done with 5 examples of esters. We now have amides. So amides have the functional group CONH2. Not amines, okay? Amines only have NH2. I've already clarified that in our initial recording for functional groups. So this one is rather simple. For amides, luckily it's easy. The suffix is also amide, as in AMIDE. So I have here 4 carbons in the parent, no carbon-carbon double bond, and then I just write the suffix, butanamide. Done. 67 is a little bit different. It's actually related to 66 because I still have 4 carbons in my parent. Although we have a double bond, so this is number 1, this is number 2, so that's 2N amide. Now, but-2-enamide or 2-butanamide only refers to this entire thing. So we didn't yet include the methyl at the nitrogen. And remember our rule on amines. If I have a substituent at the nitrogen of the amine, I use N as a locant. And that's not different in the case of amides. So we have here the prefix N methyl. Okay? So, for example, here I have, once again, an amide. My parent has 2 carbons. So that's ethanamide. Okay? And here, my nitrogen has, on top of the amide part, it has 2 methyl groups. So that's N dimethyl. And of course, we always follow the fundamental rules we've already talked about so many times, repeated so many times in part 1. 68 is another amide. So this is the real amide part. So it's also ethanamide, right? 2 carbons. Yeah, ethanamide. And then I have here two alkyl groups on the nitrogen on top of the of this one enclosed. One is ethyl, one is propyl. So in that case, you cannot use di because obviously they are not the same. So you just name them separately. N-ethyl, then N-propyl. And notice I'm following once again the alphabetization rule. Okay. Now, once again, the annoying part, what if I have an amide attached to a cyclic skeleton? Instead of just using the suffix amide, you need to use the suffix carboxamide. So here I have cyclo, 5 carbons, no double bond there. Then suffix instead of just amide, carboxamide. Oh, and once again, you have two consonants beside each other between the parent and the suffix. So you need to add the vowel there. Okay? 70, we now proceed to acyl halides, right? Because we have here COX as opposed to alkyl halides. They don't have the double bond O. So this is rather simple. The suffix for acyl halides is oil halide. So in this case, it would be oil chloride. And we have 4 carbons, once again, and no carbon-carbon double bond. And let's see, vowel, consonant, okay, that's accepted. Nothing to do here. So this is the complete name, butanoyl chloride. And for the nth time, remember that carboxylic acid derivatives are all terminal, just like amides, just like esters. No need to write number 1. Now, this is different because we have a cyclic skeleton. So once again, for the nth time, the suffix is slightly longer. Instead of just oil chloride, we use the suffix carbonyl chloride. Oh, no, it's not NMR chloride, it's bromine. It's carbonyl bromide. So from oil halide, it will be carbonyl halide. And my parent is cyclo hex, and of course the double bond is not anymore number 1. This is number 1, so this is number 2. So cyclohex to N carbonyl bromide. And once again, the old problem, 2 consonants. To solve that, we add E. So that's the final name. And the last derivatives that we will be talking about and naming are the anhydrides. And remember, their difference from the other derivatives is that they have 2 acyl groups, 2 carbonyl groups, which sort of make them look like twin towers of some sort. Now, there are 2 types of anhydrides. We have the symmetrical ones and the unsymmetrical. And it's easy to spot them. I mean, when you say symmetrical, it's the same because, for example, 72 is symmetrical because this and this are the same. In this case, it will be very easy to name them because all you need to do is to name one of them. So this one has 2 carbons, so that's F. So we just write that as ethanoic. And then this ethanoic word will also correspond to the other one. So you don't need to write any more di because we know that anhydrides have 2 of them. Okay, if ever they are symmetric. And just end with the word anhydride. So it's just like the suffix of acids, oic acid, but you change the last word to anhydride. Now, what if you have unsymmetrical anhydrides like this one, wherein one half is different from the other half? So here, you have to, of course, name them separately. So this one has 2 carbons, that's ethanoic. And then the other one has 3, so that's propanoic. And you have to remember that this one has a chloro substituent at number 2. Okay, so 2-chloropropanoic, and you have to write them separately and in alphabetical order. So this is E, this is C. Notice that I don't use anymore just the parent prefix. I use the substituent that came first. So you write first the 2-chloropropanoic, ethanoic anhydride. Okay. So yeah, I mean, you use the same suffix. In fact, you use oic for both because they're separate things. For 74, we have a symmetrical one, so you only need to write one of them because they're the same, but this time it's going to be a little bit different. Remember that this is now once again a carbon chain, and notice the headache that we've been having for these things. I mean, now you expect, hopefully you already know that the suffix is slightly different and longer, so that's correct. Instead of just writing oic anhydride, you write carboxylic anhydride. So for example, I have here cyclohexane. So you just write cyclo, hex, and then retain the suffix "ane", and then on top of that, add the suffix carboxylic anhydride. So from oic, it becomes carboxylic. And remember that this is symmetrical, so this long word already accounts for this and this. Now, if you have like a cyclic half and then a non-cyclic half, you have to write them separately. So in that case, the linear part would be the oic, and then the other cyclic part would be carboxylic in terms of the suffix. And you still have to write that in alphabetical order. I mean, you can ask me to have an example, but unfortunately, I didn't include one here. Now, we have a bonus round of some sort because we have here what you call nitriles. Hopefully, you remember them from my introduction video to functional groups. And nitriles are also carboxylic derivatives. In fact, they're related to amides. And the good thing about this is that they're also pretty easy to name. All you need to do is to first count the carbons. So that's 4. No double bond in between the carbons. An. And here, we just end with the suffix nitrile. Now, just like carboxylic acid derivatives, nitriles are terminal functional groups. So as always, you don't need any more to write the number because it's always going to be number 1. And we have 2 consonants, you put the letter E. Okay? So 76 is a cyclic nitrile. So this is the nitrile group, and then this is once again cyclohexane. So here, once again, you write the entire thing, cyclohexane. This is the chain. This is to indicate that there are single bonds. And this is E because I expect that the next letter is a consonant. Because instead of just nitrile, if we have a cyclic nitrile, you end with carbonitrile. And C is a consonant, right? So that's why we have the letter E here. So the name is cyclohexane carbonitrile. Now, just a little challenge. This is still a nitrile, so I can actually write the C triple bond N as just CN. And you should already know that that is a C triple bond N. So here, my parent chain is easy. This is 1, 2, 3, 4. So just like 75. Butane, nitrile. But this time, we have substituents. So if this is number 1, at 2, we have a chloro. At 3, we have a, what's this? It's a methoxy, okay. So this starts with C, this starts with M. So I write this first. So we have a 2-chloro, then 3-methoxy, butane, nitrile. And then 78, the last example I have for this recording, it's a fairly long one. So let's try to just name this and have more confidence as we build up on the even weirder examples in part 3. So first, I tried to look at the principal group. It's definitely this one, COOH, carboxylic acid. And that also means this is automatically carbon number 1. And then this is 2, this is 3, 4, 5, 6, 7. This one is included 8. So that's oct. Okay, oct. And then there's a double bond here. So I don't write octa. I write octe. At the double bond is number 2. So that's octo-N-noic acid. Okay, so the things that we haven't written so far are these 2 methoxy groups at 2 and 6. So that's 2,6-dimethoxy. And then remember we have OH at 5. So we write the prefix of OH, which is hydroxy. So alphabetization in consideration, hydroxy is H, methoxy is M, so I write this first. So we have here 5-hydroxy, then 2,6-di, there are 2 of them, methoxy. And don't forget that we don't consider the multiplicity prefixes in the alphabetization. So H will really come before M. So this is the complete name. Let me just double check. 5-hydroxy, 2,6-dimethoxy, oct, there's a double bond. Okay, so I think this is the final name. So I hope that you learned the basics of the functional groups. There are a lot of examples here, and we will proceed to the crazier examples, advanced rules. Prepare to get crazy if you haven't seen a lot of weird structures so far. For now, we stop here, and I hope you keep the rules really in your mind.